Hello and welcome to our second unit of AP Chemistry. I'm not sure when I'm making this video whether we are still going to be remote or not. If we are not remote, then this will be just a nice little explainer as we get started in our next topic, which is going to be aqueous reactions and reactions of what are called net ionic form. But in order to understand that, what we probably first need to really understand is the concept of solubility. What dissolves and what doesn't dissolve. And for the purposes of this unit, we're really just talking about what dissolves in water and what doesn't. I think to get a grasp on that, solubility really can mean two things. One is simply the ability to dissolve in water. And then really the sort of more nuanced version of that is, well, to what extent? So what amount of a substance can dissolve in water? And usually what we'll do is talk about that a little bit in terms of how much of the substance dissolves in water at certain environmental conditions, so temperature, pressure, all that sort of thing. But we'll get into that later in the course. So, for us, really, the first thing to simply understand is, well, how does something have the ability to dissolve in any solvent, again, specifically in water for this particular purposes? And the way that works simply is it's a result of adhesions or attractions between solute and solvent. So there should be powerful or strong adhesions or attractions between the solute and the solvent, or in these purposes, between the solute and water. So the solute and the water form these attractions and they start sticking together. What those have to be in order for things to actually go through the process of dissolving is they have to be stronger than the internal forces that each one has. So they have to be strong enough to overcome the internal forces that hold the solute together by itself and water together by itself, because water is going to make room for the solute as the solute dissolves in it and surround it in a sense. So they have to be strong enough to overcome the internal forces that sort of hold the solute and water solvent together. So once we sort of establish that idea that, well, they have to be really strong, it's certainly quite true that we get a spectrum of that process. So sometimes something has pretty weak forces holding it together, but pretty strong attractions for the solvent, and it dissolves completely. Think about something like table salt. You can put quite a bit of table salt into water and it dissolves. Quite a bit of sugar into water and it will dissolve. Some things are not as dissolvable. So if you think about putting a piece of chalk in water, the piece of chalk really won't dissolve to any great degree. A tiny, tiny, tiny bit of it will dissolve, but very little of it will dissolve. And if you drop, a chunk of lead into water, none of that dissolves. So there's certainly a range of dissolving from a high degree of solubility to virtually no solubility. And why is that the case? Well, it kind of boils down to, again, these sort of competing effects of how strongly are the two things attracted to each other and how tightly is that each of one of those substances held together by itself. And so comparing those two things, we sort of get that spectrum of results. Sometimes, again, you get complete dissolving, sometimes very little dissolving, and every result in between. And that applies to both covalent and ionic substances. So it works for covalent substances. When they dissolve, it works, and it works for ionic ones as well. So both substances can dissolve in water just fine. So, and I say dissolve now, we'll kind of get more nuanced with it as we go, but the idea is that even though they have different internal forces, which is why we classify them as different things, covalent and ionic, at least on one level, they interact with water in the same way. But because they have different internal forces, the end result is going to be different. So we have different internal forces. And as a result of having different internal forces, we get different end results. And so what we'll do today is kind of briefly look at each one. We'll talk about covalent, and what happens to a covalent substance when it interacts with water, and we'll talk about how an ionic substance would interact with water as well. So let's talk about covalent first. And maybe I'll switch up the colors here. So molecules in a covalent substance are held together by covalent bonds, right? Each molecule is held together through covalent bonds. But then how do the molecules themselves interact with each other? So in other words, if I'm looking at a chunk of wax or ice or a sugar crystal, what's holding those things together? What's holding the molecules of the wax in a sort of a squishy solid form? What's holding the water molecules in ice together in that relatively hard crystalline form? And what's holding the sugar molecules together in a sugar crystal? And those forces are not covalent bonds. So the bonds hold a molecule internally as one molecule together. But when more than one molecule gets involved, they do not bond to each other. If they did, they would just become a larger molecule. So when multiple molecules are around each other, they stick through what are called intermolecular forces. Inter meaning between, not intra meaning within. So intermolecular forces are sort of at play here. So multiple molecules are held together by what I just label as IMFs, intermolecular forces. And in the particular case of covalent substances, we talk about what are called London dispersion forces, which we'll talk much more about later in the year. And then if they're polar, they also have, and so maybe dipole-dipole forces if they're polar. So, for instance, wax just really has London dispersion forces. Water has both London dispersion forces and dipole-dipole forces, as does sugar, which is why water and sugar get along so well in terms of mixing well together, but wax does not mix well with water. So what happens then when we go to put something covalent in water, which is also covalent, the extent to which those forces are attracted to each other and are able to overcome their internal forces kind of depends on the similarity of these forces. And this is something we'll get into much later in the course. But the key idea here is that the covalent bonds are substantially stronger than these other forces. So the IMFs are much weaker than covalent bonds. So when you start pulling on the sample of all these molecules, what gives way first are these intermolecular forces, but the bonds themselves are much harder to break up. They do, of course, sometimes break, but it's the intermolecular forces that are easier to break because they are weaker. So the molecules tend to remain intact. And again, we'll talk about this as a spectrum here as well. So they tend to remain intact even though the intermolecular forces are overcome. So even though the molecules are separated from each other. So even as the molecules are separated from each other. And I'll show a diagram here in a second. So the molecules stay intact internally, but they are separated from each other. And so as you pull those molecules apart, they no longer stick to each other and they lose that sort of form that they had, but each molecule is still there. So if I dissolve sugar in water, the sugar molecules are by and large intact. A few will break up, but almost all the sugar molecules are intact. You probably remember things like that when you did the conductivity lab in intro chem. Covalent things really don't conduct electricity because they don't break up into ions because their bonds stay intact. So if we look at this from a diagram perspective, let me pull up a diagram that I think shows this fairly clearly. So here we have a diagram where the large sort of red and white things here, those represent sucrose molecules, sucrose a dimer, two sort of glucose molecules. I probably need to check on that. I can't remember whether it's exactly two glucose or whether there are other types of simpler sugars that mix together. But in any case, C12H22O11. those molecules are pretty large and quite polar, and they interact with water quite well. These little ones, all of these little things, those are water molecules. And so what happens here is, if I sort of put in yellow, there is essentially the remnants of a solid structure. See right here, it says sugar crystal. So there was a sugar crystal. This is sort of the leading edge right here of the sugar crystal as it's interacting with water, and it's going to start getting pulled apart. Now, what you'll notice, of course, is that the sugar molecules themselves over here are still intact. They were not damaged. They were just pulled away from the crystal itself. And you'll also notice that, like, the water molecules sort of had to make room for the sugar. So the water is not sort of as densely arranged in places where the sugar molecules are. So the sugar molecules, the C12H22O11 molecules, are intact individually, but they are separated from each other. That's what we call dissolving. It's sort of like, this process occurs at sort of a molecular level, that the molecular nature of the substance is intact, but the structure of the intermolecular forces, the things that hold a lot of molecules together, is getting broken due to those strong attractions, and so we sort of lose that aspect of it. So that's dissolving. Things work differently for ionic substances. The basic physics, in a sense, is the same. So the electrostatic attractions of positive and negative for one another, that still applies, just as it does here in terms of polarity. But the result's going to be different. So we use a different term. We have to talk about it a little bit differently. Okay, so how things work for ionic substances. So for an ionic substance, things sort of, you have to go back to that molecular level. Well, when you do that, in a sense, you lose some context, because ionic substances don't really have molecules. They're held together by ion-ion forces. And there's also some of those things that we call London dispersion forces, but they are much weaker in comparison to the strength of the ion-ion forces. So the ion-ion forces are indistinguishable. So in the covalent substances, you have a molecule held together with covalent bonds, and then a different set of forces holding molecules to each other, those intermolecular forces. In an ionic substance, the forces that hold one unit of the substance together and hold them to other substances are identical. So what holds one NaCl together is the same as what sticks it to all the other NaCls. So, and we'll look at a diagram here in a second, but imagine you have a positive and a negative, and then a negative and a positive, and a negative and a positive, and a positive and a negative. And after a while, it gets really hard to identify where one molecule was and where another one starts or ends or anything else. They're all sort of the same forces. And so you can't really identify a molecule in an ionic substance because there's no clear delineation of any one singular unit. There's the same unit repeating again and again and again and again, with the same forces holding them together all over the place. There's no distinguishing between, oh, well, this is an ionic bond and this is some other force. The ionic bonds, and I don't even really like to use the term, they're called ion-ion forces, they are all over this molecule. So everywhere that I'm drawing sort of green here, we've got ion-ion forces, and all those ion-ion forces are identical. So it's really hard to tell what an individual substance is versus what the collective sort of is. And so we just talk about ion-ion forces, and we don't talk about molecules for ionic substances. Sometimes they talk about the unit cell. That's actually more a three-dimensional kind of thing, or some sort of repeating unit of the compound. We'll talk about the compound, and we just sort of narrow it down to usually the lowest whole number ratio of the substance here. So these ion-ion forces are sort of a key concept here. And because there's only really one type of force, if we sort of ignore the presence of these London dispersion forces, because there's only one force, when you undo that one force, everything breaks up. So unlike the molecules where you undo the weaker of the forces, well, the weaker of the forces was the intermolecular forces, and the covalent bonds stay together. When you undo these bonds, there's nothing left. So when these bonds are overcome, there's nothing remaining of the original structure. You just have a bunch of ions floating around separately. And we talk about that as dissociation. So when ion forces are overcome or are broken, the result is individual ions. And there's no sort of molecule difference or anything else. This is all that's left with the individual ions. And we refer to that as dissociation. And it's distinguished from dissolving because what you're left with is a bunch of ions floating around, not a bunch of molecules floating around. So the result is ions floating in water, not molecules. So here we have a couple of different examples of what that looks like kind of on the particle level. So both of them show sodium chloride crystals, with the green being the representing the sodium in one and the chlorine in another, which is very confusing. And then the purple in the first one is the negative chloride ion, and the green is the chloride in the second one, which I know is kind of confusing. They don't seem to have their act together as far as which one would be which size. If you had to guess which one was correct, you should probably look at this one. The chloride ion is a lot bigger than the sodium ion is. The sodium ion, when it loses an electron, gets a whole lot smaller, but we can worry about that when we get to periodic trends. The concept is simply you start with a crystal, and then water molecules sort of begin to interact. And water molecules, because of their polarity, are attracted to the charges on the ions. And if enough water molecules kind of hit one of those ions, they can pull it apart. And you can see in this one, and I think this is actually a more accurate part, which is why some of these diagrams are better. This one has 6 water molecules around sodium. I think that's about the number they estimate is usually surrounding it. So it's called a sphere of hydration. That there are sort of this, like a bubble almost, of water surrounding these ions. And you get different numbers for different ions depending on their size and charge and things like that. So that sort of happens. And what that means really, and this is again a topic for later times, but the attraction of one water molecule for one ion is not strong enough to pull that ion out of its crystal. But a lot of water molecules, each pulling some, can win that battle and can pull the ions out of the crystal. And what we'll talk about probably in a separate video, and I'll see whether I tack it onto the same assignment or not, but there's a spectrum, of course, of this, so that some ions are very well stuck together and water has a hard time pulling them apart. Think about minerals and rocks. They're largely ionic, but water has a really hard time pulling them apart. And then there's lots of ions that dissolve very easily in water. So like table salt and things like that dissolve in water quite easily. And so there's a spectrum everywhere from things dissociating, I should say, completely, and other things really not dissolving or dissociating much at all. And why is that? Why do we have that spectrum? And so that'll be a topic probably for just a very short video that may tag along with this one or may come as a subsequent assignment. All right, thanks for watching. Still waiting on some good sign-off taglines. Hit me up, and we'll find a good one to sign off our videos with. Thanks for watching.